Yes, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, everybody. Welcome. Good evening, everyone. Here we have another session, another a very interesting session talking about JVM here with Simon. We would, on behalf of all of you, welcome our speaker. Simon, how are you?
I am very well. Salam alaikum.
Salam. Thank you so much for joining us and giving us your time. Thank you so much. Riyadh Java User Group is really welcoming everybody here to join around the world. So we are conducting online sessions mainly. So we would love also to expand this and do also in person. We did in-person sessions. Uh, in the beginning, we would like to give a little bit introduction about our guest, Simon. He is a really well-known worldwide speaker. He speaks for different occasions. I have seen his talks in Belgium DevOps and
Mhm.
also UK DevOps. So we have a very unique figure over here. And also works for Azul. Azul is really one of the, I think, if not one of the organizations, I mean, specialized into the JDK and the performance and how to make Java performing well. Of course, I will leave this introduction to Simon. Guys, please make sure that if you have preparing, we would like you to prepare a very tough questions for our guest. Yeah, if you have any questions, please drop them in the box below. And the session is already recorded and live streamed now in YouTube channel. You can visit anytime and check the recording. Without further ado, so I will leave the stage for our guest. Thank you so much, Simon. Good luck.
Great. Thank you very much. Yes. So welcome again. As we already said, my name is Simon Ritter. I'm the Deputy CTO at Azul. Azul is a company that focuses purely on Java, and we do Java runtime. So we're not actually Java source code for applications. We just do Java runtimes. What I'm going to talk about today is, as the title suggests, how you can improve the performance of your JVM-based applications. So I'm specifically talking about JVM-based applications, which means it doesn't have to be written in Java. It could be written in Kotlin, it could be written in Scala, Clojure, any of the languages that compile into bytecodes. You can then run those, but get better performance without changing any code. So let's talk about how we can do that. First thing we need to understand is what we mean by speed in the Java world. And this is quite important. And when I sat down to put these slides together, I thought to myself, okay, let's have a graph which shows what is the perfect speed we would expect from the JVM. And the graph I came up with was pretty simple. As you can see here, what we want is a graph which starts off when we start our application, and the JVM can deliver 100% of the performance immediately. So there's no waiting for anything. We can deliver 100% of the performance that we can get all the way through we're running the application. That's what we would like. The reality looks somewhat different. And if I show you a typical performance graph, so this is random application, typical performance graph, this will vary depending on what you're doing, but this is something we very frequently see. This is very different to the perfect graph that I showed you a moment ago. And let's dig into this in a little bit more detail to understand what it is that's going on that's causing our performance to vary in this way. Now, obviously, when we compile our Java applications, what we get are bytecodes. And bytecodes are the instructions for a virtual machine, the Java virtual machine. The thing about that is that they're not instructions for the real machine that we're running our application on. This is the whole idea behind write once, run anywhere. How Java can take the same class files, the same jar files, and run them on any machine, whether it's an ARM-based processor, Intel-based processor, Spark processor, whatever, different operating systems, the same class files run on any machine. But that's because we have to make a conversion between those bytecodes and the instructions for the machine that we're running on as we run the application. And at the beginning, we run in what's called interpreted mode. Interpreted is where we take each bytecode in turn and we say, how do we convert that into the necessary instructions for the machine? In some cases, that's going to be very simple, because if you're doing something like an OR operation, doesn't matter really which machine you're on, that'll be a single instruction for that particular platform, and it's a very simple conversion. But for more complicated things where you're actually, for example, invoking a method, that's a lot more complicated and requires a lot more instructions. So we have to do that every time we see a bytecode. There's no kind of remembering anything. And that means that we run very, very slowly compared to what we can do. And this was one of the things when Java was first released 30 years ago. People complained about the performance. They said, Java runs much more slowly than if you take an equivalent C or C++ natively compiled application. They run very differently. So we found a solution to that. And the solution was what we call just-in-time compilation. Just-in-time compilation essentially says, right, as we're running the application, we'll keep track of all the methods that we call, and we'll count how many times we call them. When we find there's a method that we call, let's say, 10,000 times, we know that this method's being used frequently. Rather than processing the bytecodes every time we go through that method, let's take that method and pass it to a compiler that's built into the JVM. That compiler can then generate native instructions for the whole method, and then we can run that and it will run faster. Now, this happens in a number of stages. And the first one, as we can see here, is what we call C1 JIT compilation. C1 JIT compilation is all about taking that method and compiling it as quickly as possible. But we don't really optimize it very much. We can do some basic level of optimization, but we can't do more complex things. What we then do is we let that piece of code run, but it also includes instructions that allow us to profile how that method is being used. Once that method gets used more and more, then we get to a stage where we're going to use a second JIT compiler. This is the C2 JIT compiler. Now, the C2 JIT compiler takes the same method, same bytecodes, and then compiles it again. But this time, because it's got profiling information, which shows how that method is being used, we can take a lot more optimizations and make it perform a lot better. The drawback is that we can also sometimes get what are called de-optimizations. De-optimizations are where we make an assumption about how the code works based on that profiling information, but sometimes that assumption turns out to be false, and we then have to throw away the code and recompile it based on a new set of assumptions. So this is where we see dips in the performance as we start to get to a higher level, and that's where we're throwing away code and having to recompile it. After a while, we'll get to our steady optimized state. So this is the situation where we've taken all the frequently used methods, we've compiled them with C1, we've profiled them, we've compiled them with C2, and wherever the optimizations have occurred, we then recompiled them and made everything work. So that gives us our sort of optimum level of 100% performance. But we still see some dips in performance there, and those are due to a different aspect of the JVM. That's where we see garbage collection pauses. JVM handles memory management for us automatically, and one of the things that it does is recover object space when we no longer need those objects. The problem is that most garbage collection algorithms, the way they work is to say, well, in order to move an object within the heap safely, what we don't want is for an application to be changing that object as we move it. To do that, we will simply pause all the application threads, do the work of moving objects around within the heap, and then restart the application threads. This leads to some dips in performance because we're pausing our application. So the challenges that we have in terms of the JVM all come down really to the fact that it's a managed runtime environment. We're not taking a set of source code, compiling it into native instructions, ahead of time static compilation. We're using this dynamic nature. And as we've already kind of explored with that graph, one of the big things is how the garbage collector works. Garbage collector is inherently non-deterministic. We can't predict when the garbage collector is going to need to run because it all depends on how many objects we allocate, which will depend a lot on how the application is being used. So there's no simple way of figuring out when the garbage collector is going to run so that we can take action to minimize any impact that has. The other problem we can have is that pause times for a garbage collector can be big. Now, if you're lucky, they could be of the order of like milliseconds, tens of milliseconds, hundreds of milliseconds maybe, but they can be a lot bigger than that. We can see pauses which could be seconds. We could see pauses which could be minutes even. The longest pause time I ever came across was one very, very, very large heap where they were having a pause time of 1.5 days. Now, that's an extreme situation, and there are things that you can do to alleviate that. But that is the problem we face with garbage collection. Pause times typically are dependent on the size of the heap, not how much data you have. The second thing is the idea of bytecodes. Bytecodes are not machine code, so we have to go through this adaptive compilation. We have to go through different strategies depending on whether it's C1, C2, profiling, de-optimizations, all of those sorts of things. And the other thing that leads to is that graph that we saw where we had a gradual increase in performance, and that's what we call warm-up time. How long does it take from starting the application to getting to the point where we've got 100% of the performance that we can get from that application? Again, that can vary in terms of time. It could be a couple of minutes, it could be a couple of hours. Depending on what the application is doing, it could be longer than that. So what if there was a better way of doing things in the JVM? And that's what I'm going to talk about for the rest of the presentation, which is what we've done at Azul, which is what we call Platform Prime. Now, don't worry about this. It's not a sales pitch. I'm not trying to sell you on using this, although obviously if you're interested in this afterwards. This is very much technical exploration of what we can do in terms of changing the way the JVM works. So what we're talking about is Azul's Platform Prime. The first thing to understand about Platform Prime is that it is identical in many ways to what you're using already in terms of Java. We decided that it didn't make sense to start from scratch and rewrite the whole of the JVM. Didn't need to write the whole JDK as a new version. So we said, let's start with the open source version, OpenJDK, and then we'll make some changes to it internally, which will give us better performance in terms of garbage collection, in terms of the way JIT compilation works, and in terms of warm-up. But very important is we don't want to have to change any of the application code. No changes to application code, no changes in terms of recompilation. So we pass all of the tests which are required to show that a JVM and a JDK complies with the standard, which is defined through the Java community process, through what are called Java specification requests, or JSRs. What that means is it is a drop-in replacement for other JVMs. No change to code, no recompilation. What we've done in terms of the changes is initially look at how garbage collection works. And we took all the garbage collectors that were available in Hotspot, which is the JVM in OpenJDK, and we said, let's just remove all of those. So no more serial collector, parallel collector, G1, CMS, Shenandoah, ZGC, just take them all out. And replace the one that we call C4. And I'm going to explain what C4 is and how it works in a moment. Now, another very important thing about how our garbage collector works is that we've tried to do some very clever things underneath the JVM. And because we've done these clever things underneath the JVM in the operating system, it means that we only support it on Linux. There isn't a Windows version, there isn't, well, there is actually a Mac version, but we only support it on Linux for production systems. The second thing that we did after looking at garbage collection was figure out how could we improve the way the JIT compiler works. Now, if you look at C1, because it compiles quickly and doesn't do a lot of optimization, there's not really a lot you can do to improve performance there. C2 is the thing where you can get a big win. And so what we've done is replace C2 with a different JIT compiler that we call Falcon. And again, I'll explain what we do as we go through the rest of the presentation. And then we have what's called Ready Now, which is warm-up elimination technology. How can we reduce that time that it takes to get to the steady state of performance as much as possible? A little bit more about the Zing system tools. This was the thing that we put in underneath the JVM. So it essentially was a kernel module that you could use on Linux to replace part of the memory management system in Linux. This allowed us to do some quite clever things in terms of understanding the cache status of the way the physical memory is being used. We could do some interesting things in terms of how memory is mapped between the heap and the underlying physical memory, and be able to use that memory more efficiently. And we could also have what's called contingency memory. Contingency memory meant that if you had assigned 8 gigabytes as your heap size and you got to the point where you were about to run out of heap, rather than throwing an out of memory error, if we had enough memory still available, we'd actually allow you to go beyond 8 gigabytes, and then we'd start running the garbage collector to bring things back under the 8 gigabyte limit. Because of the way Linux has changed, there's now what are called transparent huge pages, which we can use as an alternative to this, so we don't need a kernel module. If you're using less than 1 terabyte of heap, then you don't need the Zing system tools. If you want to go above 1 terabyte, we go all the way up to 20 terabytes, then Zing system tools are still needed. Let's talk about the garbage collector then. I said it was called C4, and that stands for the Continuous Concurrent Compacting Collector. And essentially, that describes what it does. It runs continuously, so it's running in the background, keeping track of how much memory is being used. It is concurrent, so it allows the application threads to run at the same time as the garbage collector, even though we're compacting, meaning that we're moving objects around within the heap. But we can do that completely safely, so that you're never going to get a situation where you've got inconsistent data, or you've made a change in one place and it's not being reflected when the object gets moved. And of course, it is a collector. So that's why it's called C4, Continuous Concurrent Compacting Collector. A little bit about the basics of how C4 works. First thing is it is generational. Now, what I mean by that is that a lot of garbage collectors will divide the heap space into different regions called generations. And typically it's 2 generations, young and old. There's a very good reason for this, because if you look at the way most applications, and I do mean almost every application, allocate objects, you'll find that most objects only live for a very, very short space of time. It's what's called the weak generational hypothesis. Because of that reality, if we can collect most objects in the young generation, we can reduce the load on the old generation. So where there are objects that survive for a longer period of time, we can make it much more efficient if we have both a young generation for getting rid of those short-lived objects and the old generation, which we can manage for those ones which survive for longer. In the case of C4, unlike other garbage collection algorithms, we use the same collector for both the young and the old generation. If you look at things like the G1, it uses a different algorithm to collect the young generation to how they handle the old generation. We use the same one. As I said, it is fully concurrent, meaning that there are no pauses associated with having to stop the application threads to do work of the garbage collector. Fully concurrent. It is also parallel, meaning that we can have multiple threads doing the work of the garbage collector at the same time that we're running the application. And as I said, very importantly, it is compacting, meaning that we can eliminate the gaps between live data and reduce fragmentation in our heap. Again, very importantly about the basics of C4 is it does not have a stop the world compacting fallback situation. If you look at something like G1 as a collector, it's very good in low loads for the garbage collector. But if you push it to the absolute limit, it will sometimes get to the point where it says, okay, we can't keep up with this. We have to do a full stop the world compacting collection, and that can take a lot of time. So there are situations where that will happen. With C4, that will never happen. In terms of how the algorithm works, it's 3 phases: mark, relocate, and remap. And we'll explore what those do in a moment. Now, the important thing about this is how can we do the work concurrently when application threads are still making changes to objects? So if they're changing values that are stored in an object whilst we're copying it, how do we do that safely? And the way we do that is using what we call a loaded value barrier. And it's essentially a read barrier, meaning that every time you access an object, we will intercept that reference, and we will look at the object header to understand what the state of that object is in terms of the garbage collection. What we can do then is we can enforce two rules on how things are working. The first is that when we're doing a marking phase where we're looking for objects that are still in use, we can guarantee that any object you get a reference to will be marked, meaning it will be identified as an object that is still in use. That way we won't miss anything as we're going through the marking phase. When it comes to the relocation and remapping phases, we also guarantee that any reference you get to an object will point to the correct place where you can make changes without losing them. So that again is very important because we don't want inconsistent data. So this allows us to do fully concurrent marking, fully concurrently relocation and remapping. What most people will ask me then is, well, if you're intercepting every object reference, doesn't it have an impact on performance? And the reality is, yes, it does, and no, it doesn't. Yes, it does because we have to do something, but no, it doesn't because the impact of that read barrier is very, very small. Essentially, what we're doing is we're doing two instructions in terms of the processor, a test and jump. We look at bits in the object header and we say, what's the state of that bit? If the state of that bit is something that requires us to do some work to ensure that the object is marked or the position is correct, then we'll jump to a handler. But most of the time we won't need to do that. So it's test and jump, two instructions. And on a typical x86 architecture, that's a single micro operation at the processor level. The impact of that is then realistically less than 1 nanosecond per object reference. So you really won't find that for any realistic application, there'll be any impact on performance. The fact that you need to reference the L1 cache, the L2 cache, the L3 cache, main memory, that will far exceed any impact that you get in terms of this read barrier. How does it work? Okay, so the first thing we need to do is a marking phase. And the marking phase is, as I said, where we're going through and we're saying, let's identify all of the objects that are still in use. Because we identify the ones that are still in use, then we can identify where we've got gaps and where we've got space that we can reclaim. To do that, we use a very similar algorithm to a lot of other GCs, which is to create what's called a root set. The root set is essentially looking at all the references we have through objects on the stack, the registers and so on, and we'll say, what are the immediately accessible objects that we have? Clearly, those objects will have references to other objects. So we need to trace through the graph of object references that we have to identify every single object that's still in use. To do that, we'll have our garbage collection threads that will start working on the root set. And they'll take the first object in that root set and they'll set a bit in the object header to indicate this object is still in use. We'll then start following the links from that object to other objects and setting the bit in those. So we'll mark those as in use. Now, because we have multiple GC threads, we can also do this in parallel. This is actually very easy to decompose into a lot of independent tasks because the root set doesn't have any links between different objects. So we can do that independently and we can do that very effectively. So we can have multiple threads running on the root set. Our application threads, remember, are still running concurrently. So they're still doing work. Now, at some point, our application thread is going to access an object. At that point, we do our test and jump. We do a test on the bit to indicate that this object is marked. If it is marked, then we don't need to do anything and we can just return the object reference to the application and it can go on doing what it needs to do. But if it does need to be marked, what we'll do is then we'll jump to the handler and the handler will effectively do a small piece of work, which is what the garbage collection threads are doing. And it will set the bit in the object header to indicate this is still in use. Obviously, there are going to be links, most likely from that object to other objects. We don't want to have the handler follow those links, because that could be something that would take a long time to do. So to get around that, we simply pass the object to the garbage collection threads and say, make this part of the root set and let it follow any links from there. Obviously, if the application follows those links and starts accessing the objects, the same thing will happen and we'll mark the object as in use. The net effect is that what we're doing is we're marking every single object, and we're guaranteeing that any object that's given to the application thread during the marking phase will be marked. We're not going to lose any references. What we then need to do is the relocation phase. And this is where we're going to move objects around within the heap to compact and make sure that we've eliminated fragmentation. If we look at the top part of the picture here, we've got 5 objects spread out through our heap. So we've got A, B, C, D, and E. In order to compact those, what we're going to do is we're going to copy each of those objects to a different part of the heap and make them contiguous. So now we'll have A prime, B prime, C prime, D prime, and E prime, all contiguous. We've eliminated the fragmentation. We can copy those and we can put a lock around the copy operation so that whilst we're doing that, objects aren't going to get updated by the threads. So there are no pauses for the work of the garbage collector, but we will have very small pauses in there as we move it or copy an object around. But again, that won't create any significant pause that we would see in terms of our application. The other thing that we need to do is we need to have a copy in terms of the data to say where has A been moved to and where has B been moved to and so on. What we'll do is we'll create a side table which has the details of where A has been moved to A prime, B to B prime, C to C prime, and so on. What we can then do is we can also use our ability to handle memory underneath the JVM to do some clever things. And this is what we call quick release. So you've got virtual pages and you've got physical pages. And there's a mapping between the address space of the virtual pages and the actual physical pages of memory in the machine. Now, if we need a page to continue our garbage collection, so you can see that the second block on the bottom there doesn't have a physical page mapped to it. Because we know that the first page on the top part is now no longer ever going to be used because we'll only reference objects that have been copied to the new position, we can actually steal that page from underneath and move it so that we can reuse it for copying new objects there. And we can do that as we want to for further pages that we require. The net effect of this is that it means we can actually do a full collection on the heap, no matter how big it is, all the way up to 20 terabytes, and we only need one free physical page of memory for each thread that we're going to use in the garbage collector. So we can let the heap space go to almost 100%, and we can still garbage collect everything without any problem. Finally, we have the remapping phase. And what happens here is that we need to update the references in the object headers to represent where the new position of those objects is, where we copied them to. To do that, our garbage collection thread will look at the side table and it will say, okay, so A has been moved to A prime. We need to update that in the reference to A. So what we'll do is we'll change the address in the object header for A to point at A prime, and then we'll also set a bit in the header to say we have now updated that. We can do that with multiple threads, but then we have the application threads also doing work. So at some point we'll access an object, and then again we're going to do our test and jump. We'll look at the bit in the object header, and if it hasn't been set to say this object has been updated, then our handler will look at the side table, retrieve the new address, copy it into the object header, effectively doing the work of the garbage collection thread, set the bit to indicate that work has now been done, and then pass it to the application. The application is guaranteed to always get the right place for where it can make a change so that the change is not lost. So that's how we can do fully concurrent garbage collection, no matter how big the garbage collector is. So what this does is it means we can deal with big heaps without any problem. As I said, it scales all the way up to 20 terabytes, and you don't see any degradation in pause times as you increase the heap. And that's something you don't see with other garbage collection algorithms. This is also very good because we see a lot of customers who actually break up a big heap into multiple small heaps to try and minimize garbage collection pauses. So now you can just do everything in one big heap and make your application more efficient from that point of view. Don't have to have a big heap. You can scale all the way down to 512 megabytes as a minimum. Realistically, we want 1 gigabyte, but we can go down to 512 megabytes as a minimum heap space. Let's talk a little bit about GC tuning, because people spend a lot of time and a lot of effort trying to make the garbage collector work the way they want it to. The reason for that is that there are lots and lots of garbage collection tuning parameters. And I've created this sort of diagram here, which shows not probably all of the different parameters that you can change in terms of garbage collection. There are literally dozens, if not hundreds, that you can change. And what that means is that you end up with things like this. And these are two examples that I've taken from real world customers that we've worked with. Now, I don't want to go through all the details of this because obviously there's a lot of different things being done here, but you can see how complicated it is to try and configure a garbage collection to make it work in the way you want it to. But I will just highlight one thing here, which is that both of these examples, they've set what's called the survivor ratio. And that's to do with the young generation, and within the young generation, you have an Eden space and 2 survivor spaces, and you can set the ratio of the survivor space to the Eden space. What's interesting here is that the first example, they've set the survivor ratio to be 128. So survivor space is going to be quite small. In the second example, they've set the survivor ratio to be 2, which means survivor space is going to be very big. What's the correct value for that? Now, there isn't an easy way to say, well, if you're doing this particular type of application, set it to 64 or set it to 32. What you end up doing is setting it to a value, seeing how your application performs, then changing it, seeing if it performs better, changing it again, and trying to find the optimum value for that particular parameter. If we only had one parameter, that would be fine. But there are multiple parameters, as I said, and that means you end up with an n-dimensional space where you're trying to find the best fit to give you the best possible performance. Let's look at what you would see if we take exactly the same kind of applications, and this time we'll run them using Platform Prime and the Zing JVM. Well, that's it. That's all you have to do in terms of tuning with Prime. You simply set the size of your heap space and you let the Prime algorithm do what it wants to do internally, and it will adjust things to figure out the best way of optimizing things. What we then say is, okay, set the nice big heap, work your way down until you kind of run out of performance, and then increase the heap space a bit to give you some headroom, and that's really all we have to do. To be fair, there are some tuning parameters we can use, like changing the number of garbage collection threads that are being used, but there are only a handful really that you would use to change the way that the garbage collector works. Now, how can I show that this actually works? What we did was we created a small open source project for measuring the performance of the JVM independent of the application, because you don't want to see how the application is performing. You want to see what's the performance of the JVM when it's running your application. To do that, JHiccup, as we call it, is where we add a thread in the JVM alongside your application, but it doesn't interact with the application code. And to avoid the problems of it impacting performance itself, it spends most of its time asleep. Essentially what happens is when we start the application, it will go to sleep for 1 millisecond. When it wakes up, it looks at the system clock and says, I expected to wake up 1 millisecond later. What time did I actually wake up? So if you have a garbage collection pause that pauses application threads for 20 milliseconds, when it wakes up, it's going to see a 20 millisecond delta, woke up 20 milliseconds later than it expected to, so it can record that information, put it in a log file, create some histograms, and then we can graph that to show how things are working. Let me show you an example. Here's a reasonably big heap. This is an Elasticsearch application running with 128 gigabyte heap. On the left, we've got hotspot, and this is showing a very typical graph that we would see with hotspot running G1, for example. Lots of small spikes, which are indicating minor GC pauses, so that's the young generation getting collected, and then 2 big spikes, which is where it's doing a collection on the old generation or a major GC. On the right, I've shown a graph which is showing how the same application runs on the same machine with the same workload. All we've done is change from using hotspot to using Platform Prime and the Zing JVM. Now, if I tell you that the big spikes are bad, you might look at that right-hand graph and say, okay, you're saying that's better than the left-hand graph? I don't really see that. Well, I've been deliberately misleading, and I've scaled the graphs differently. So if we look at the left-hand graph, that's 0 to 8 seconds, or 8,000 milliseconds, meaning that the small spikes are about half a second, the big spikes about 5, 6 seconds. So fairly big pauses. On the right-hand side, I've scaled it from 0 to 80 milliseconds, so 2 orders of magnitude different. If I scale the graphs the same, then we really see the impact. And we see that all of those garbage collection pauses just disappear. We have eliminated all the problems of latency running that application. Now, I did say that we don't depend on a big heap. So here's a different example. This is running Hazelcast on a 1 gigabyte heap. And again, we can see that in this case, we've got a quite badly tuned application where we're doing a lot of almost continual young generation pauses, somewhere in the region of 25 to 40 milliseconds, I'd say, but that's going on almost continually. And if we switch to using Prime, again, we literally eliminate all of those. We're getting 1, 2, maybe 3 millisecond pauses that are not necessarily due to GC. They are actually more likely to do with the way the operating system is running underneath when you get down to that level. Okay, let's talk about JIT compilation and what we've done differently there. So the idea behind Falcon, as we call it, is to replace the C2 JIT compiler. And we looked around and we said, okay, is there something that we can use to start this project? And we found that there's another open source project called LLVM. It's all about compiler technology. It's a very well supported project, lots of engineers who work on it. There's people from Microsoft, there's people from Apple, there's people from NVIDIA, Intel, ARM. All the people who you would expect to understand compilers are working on this project. What we did was we took that code and we said, let's use it, because it's essentially the back end of a compiler that takes intermediate representation and generates optimized code. Let's take that, integrate it into the JVM, make it work with the garbage collector and the other parts of JVM, and then have it run as our JIT compiler. So we did that, and then we put the code back to the project so other people would use it if they wanted it to. What that allows us to do is to get more heavily optimized code from the same method. So we're taking the same set of bytecodes, but what we're doing is generating more heavily optimized code than you'll get with C2 in Hotspot. Give you an example of how we can do that. If we look at a very simple piece of code here, what I've got is an array of numbers being passed to a method, and I want to add up all the numbers in that array. Okay, that's fine. And a modern compiler will look at that and go, we can use what are called vector operations. Vector operations are single instruction, multiple data. Use very wide registers that are supported in all modern processors. You can load up multiple instances of the elements of your array, apply a single operation to all of them at the same time so that you get true parallelism and you get multiple elements handled in a single clock cycle. It's great. Improves performance of numerically intensive operations. However, the problem comes when you start making the code more complicated. Just adding up the elements in an array is great, but as soon as you introduce something like a conditional, so an if statement, and in this what we're doing is we're saying, okay, we've got 2 arrays now, and we want to add the elements of the second one to the elements of the first one, but only if the second one is even. Okay, as soon as we do that, most compilers will then run into a problem. They'll go, ooh, can't see the way to use vector operations for that. Whereas with Falcon, we can. So if I show you the code that's generated by C2, traditional JIT compiler, don't worry about all the instructions and things. This is running on an Intel processor. The important thing to see here is the red rectangles. What we're seeing there is the big red rectangle indicates the body of the loop, and the 2 smaller rectangles indicate where the optimization that's handled here is through what's called loop unrolling. So we're doing 2 elements per iteration of the loop to smooth things out and make it more effective. But that doesn't really make that much difference to the performance of that loop. If we look at the code that's generated by Falcon, it looks very different. It's got a much bigger rectangle on the outside, so you might think, oh, well, that's not as good. But what we're doing here is we are using vector operations. And on the particular machine that we tested this on, what you've got is AVX2 instructions, meaning you've got a 256-bit wide register that you can use. In addition to that, we're doing more loop unrolling. So we're actually doing loop unrolling with 4 elements per iteration of the loop. So the net effect of that is that we're doing 32 elements each time we go through the loop, and 8 of those are being done in parallel in a single instruction cycle. So we get much better performance for that kind of operation. How that translates into real world is something that we can show in terms of running benchmarks. So what we do here is we take a machine, we set it up to run a benchmark for a particular piece of software, we run it with Hotspot, we measure the performance of that, then we switch to using Platform Prime with the Zing JVM, we run it again with the exact same workload, exactly the same machine, and we see what the difference is. Here you can see that Kafka, which is really our sort of poster child for the best performing application we have, that will get 53% or nearly 54% more transactions per second than you get by running Hotspot. That's just by changing the JVM. When we talk to people who are running large Kafka clusters with large numbers of machines and large instances, especially in the cloud, this is a huge difference. 54% more transactions per second means that you can deliver the same load carrying capacity, but you can actually reduce the amount of machines and the size of the machines you need, probably in the region of somewhere between 20 and 30%. And that's a big saving in terms of your cloud bill, just by changing the JVM. Other benchmarks, as you can see, Cassandra is another good one. That's nearly 30% better. Renaissance is a sort of broader set of benchmarks. That's 42%, nearly 43%. Other things, basically what I'd say here is your mileage will vary. It depends on what the application is doing as to how much of an improvement in performance you can get. But this gives us sort of an idea that you're not going to be seeing, hopefully, you're not going to be seeing like 1-2% improvement of performance. We're talking 10, 20, 40, 50% improvement in performance. Ready now. How do we reduce warm-up time? So what we do here is, rather than changing the way things work directly internally in the JVM, we say, okay, let's let the application run and let it warm up to the point where you're happy with the performance. What we'll then do is we'll take a profile of that running application. And that will be a list of all the classes that are loaded, all the classes that are initialized, all the profiling data that was collected when we did the JIT compilation, and all those speculative optimizations which failed and we had to throw away code and recompile it. We can gather that over whatever period of time you want. So it could be minutes, could be hours, could be days if you want, or even longer. And that allows us to then eliminate the problem of the optimizations, get that warmed up code ready to go. What we can then do is when you start the application again, you can do all that, almost all of the work of getting things ready before you get to your main entry point where you start your application code. So you'll load the classes, initialize the classes, compile the code that you need, all before you get to main. Typically what we would see is about a 98% of the performance you had when you took the profile. There's certain things we can't do because of the way the JVM is defined, which means that we can't quite get to 100%, but after a few transactions, you'll be at 100%. Again, sort of performance graph. If we look at this before Ready Now, we'll see like a lot of warm-up time and activity as the system warms up. That's the orange line. When we use Ready Now, we see a blue line where everything's nice and smooth and it's no problems in terms of latency. Now, if I look at the first graph that I showed you, the sort of idea of how we see warm up, and I just simplify that into a triangle and a rectangle, this is what we see without Ready Now. If we look at the same thing with Ready Now, we see a different profile. So now we're seeing a much steeper graph in terms of warm up, and we get to that optimum level of performance much, much more quickly. However, a little bit of a problem, which is that there's this blank spot where the application is not doing any work at all, and that's because of class loading, initialization, compile time, and so on. So it's what happens before we get to main. For a lot of people, that's not a problem. If you're running like a trading system, then you would just start the application 10 to 9, and then by 9 o'clock, everything's ready, and you don't have a problem. But we thought, how can we improve on that further? So what we did was we looked at the way the pipeline works, and essentially what's happening is we've got the bytecodes, we pass it into LLVM as the compiler. That will then send some queries to the virtual machine to understand the profiling that's been done, gets back some responses. Based on that, it will generate some optimized code. What we found is that the compiler is fully deterministic, meaning that if you have your initial intermediate representation, IR, intermediate representation, so the bytecodes and the profiling data, what you'll get is the same queries and responses from the compiler to the VM. So you've got identical input, and what you'll get back is identical output. So regardless of how many times you put the same things in, you get the same thing out. What that allows us to do is say, well, okay, let's now put a cache in between the compiler and the VM. So that now what we can do is we can say when we need the code, rather than having to compile it every time, we can just go to the compile stash or the cache and then recover it from there. And that will allow us to take that period of time where we're not doing any work, and we can reduce it by up to 80% in terms of compile time, and also reduce it by 60% in terms of the CPU load. So that solves a lot of that problem. Now, the last thing I want to talk about is something else that we've done more recently, which is looking at the issues of how we can improve performance, but some of the sort of side effects of that. Because the reality is that better performance has cost. What do I mean by that? Well, here, again, we've got some graphs. And in this case, we're looking at a small container, 2 vCores. Doesn't really matter too much how much memory it is, but we've got 2 vCores. When we run an application, sample application on there using Hotspot, we can see this orange line was generated. So we're seeing quite fast startup, getting to our optimized state. That's the top line. The bottom line is where we're seeing CPU load. And the CPU load is quite heavy to start with because we're doing the compilation, and then it drops off when we finish compilation and then we're running the application. But we can see that for the first part of the run, we're actually kind of thrashing our 2 vCores to get everything done and do some application work, and then it drops off. If we look at the same thing using our Falcon JIT compiler, it looks very different. If we just concentrate on the top graph and we say, well, let's look at the right-hand side of that graph, we can see good things because we can see the blue line is significantly higher than the orange line. That means we're getting better throughput than we get with Hotspot. That's really good. So maybe 20% there, maybe 15, 20% improvement in performance, which is really good. But if we look at the left-hand side of the graph, it's very different in terms of its profile. It takes a lot longer to get to warm up to any sort of steady state. And even when we get to the higher steady state, there's a lot of dips in there, which is where, because we're using more speculative optimizations to try and get more aggressive in terms of the performance, we also see more de-optimizations. And that's where we see dips where we've had to throw away code and then recompile it again. If we look at the bottom line, the blue line is also much higher for longer because we're having to use more processing power to do the compilation. And that has an impact on how much we can do in terms of the application workload. So it's a sort of double whammy that we're hitting there. What we said was, okay, how about if we take the way that the JIT compiler works and let's decouple the JIT compiler from the JVM. Let's take it out of the JVM and turn it into a JIT as a service. Pretty much everybody's running in the cloud at the moment. Even if you're not, we can set this up in your own data center. Let's make the JIT compiler into what we call the cloud native compiler. Set it up as a service. So when a JVM needs to compile some code, rather than doing it locally, it passes the method bytecodes plus the profiling information across the network to the cloud native compiler. It does the compilation and then passes it back to you. Great. If we look at the results of that, what we can see, okay, this is our graph as we saw it before, where we've got the orange line that represents Hotspot, we've got the blue line that represents Falcon if we're doing the JIT compilation locally. Now I'll overlay that with a green line, which will show you what we get in terms of Falcon, but running it on the cloud native compiler. If I drop out the blue line to make it clearer what we're actually seeing, we can now see a much more ideal graph, because now we've got the same speed of warm up as we get with Hotspot, but we get to that optimum level, which is 15 to 20% higher, much more quickly than we did before. So we've got a much better profile in terms of the graph that we saw for the actual workload. And then even if we look at the CPU load, we can see that because we're doing all the compilation remotely, the thrashing of the processor drops off very quickly. And you could even argue that with a situation like this, we might be able to get away with reducing that to 1 vCore rather than 2 and still run our application without any problems. So you can see the benefit of shifting the work from the individual JVM to the centralized service. Just to summarize then, basically what we can see now is two profiles for our speed graph. So the first one is the one that we saw earlier, where you've got the yellow part, the green part, and the light blue part. Same profile we had before. Then what I've done is I've kind of overlaid that, or behind it is the new graph, which we would see with Platform Prime. And so effectively what we're doing is we're eliminating the pauses that we got from the garbage collector by using C4. So we can eliminate those, don't need to have application pauses, we can do all the work concurrently. What we're then doing is shifting the maximum level of performance up by using Falcon, applying more optimizations like aggressive vectorization, all sorts of different things that we can do in addition to that, but we can get better performance overall. And then by shifting the workload out, we can use Ready Now and we can use the cloud native compiler to make that profile much better in terms of the steepness at which we can get to our optimum level, how quickly we can get to that optimum level and avoid those de-optimizations. So now we've got very close to a perfect graph, and in fact even better than we would have had with Hotspot, even if we didn't have those issues. But we get very close to the idea of a perfect graph for the performance level. So this is really how we can improve the performance of our applications without changing any code, just by changing the JVM. So that's my presentation. So what I'll do is I will throw it open, see if anybody has any questions. I'll just stop sharing that there. So
thank you, Simon. It was really interesting presentation, very detailed. Thank you so much. There's a couple of questions, if you don't mind.
Sure.
So yes. Why there is no we are now in the AI part and AI world, why there is no like AI embedded agent into the JVM itself and to make it out of the box like
yes,
performance?
it's a very interesting question, and there's a number of answers to that. There were some people who started doing some work on that. There was a company called JClarity, which existed probably about 5 or 6 years ago. And Martin Verberg, who now works for Microsoft and runs their JVM team at Microsoft, he started that company. And they were looking at specifically that idea of using AI and a training model based on the information they could get from the JVM to actually do tuning of a JVM based on using the ideas of AI. That didn't really kind of work as well as they hoped it did, but I know that now we have a lot more sort of work that's gone on, especially with like large language models, LLMs, and things like that, that people are looking much more at, okay, how can we use the information we can get from the JVM as a training model and then use that to adapt the way the JVM works internally to make it perform better. And I know we at Azul are actually looking at some of that internally. We've got some sort of research projects that we're working on, but it's one of those things that's never quite, it sounds really simple when you say, oh, let's just use AI on the JVM and make it tune it. That's really easy to say, but it's really difficult to actually make it work. So yes, there is definitely work going on there, but it's a longer process than maybe some things that are easier to do with AI.
Yes, thank you so much. So there is another question that if we are not, if we are in the normal JVM runtime, can we use parts of the Azure like tools like the Falcon or the C4 or other type of components? Yes.
Yeah, the simple answer to that is no. And we have looked at that, whether we could do sort of like a JVM with only C4, a JVM with only Falcon. but it just doesn't really make sense to us. It's either sort of all or nothing. I mean, you don't have to use Ready now, so you could just run Zing with C4 and Falcon internally and not bother using a profile for Ready now, and you don't have to use the cloud native compiler either. So there is some flexibility there, but it's really, you either use OpenJDK with Hotspot or you use Platform Prime with the Zing JVM that has the different internals in it.
Awesome. There's also a question really coming to my mind. So we see very interesting stuff Azure really has already like provided and sold. So why these very interesting, amazing solutions not adopted by the Java itself, and not taking this as make it like this is our new JVM?
Yeah. No, that's a very good question, and we have seen some things around there. So to give you an example, so we created C4 probably, but maybe 15 years ago. So C4 came out 15 years ago, and the real CTO of Azul, Gil Tene, he wrote a paper which explains how C4 works from a sort of high level, but it's very technical. And that was published, and lots of people read it, and that was fine. A few years ago, some engineers at Oracle decided that they'd take that paper and then they'd create a different implementation of the same algorithm. So that's essentially what ZGC is. So if you look at ZGC in Hotspot that you can now get, then it's based very, very heavily on the C4 way of doing things. It isn't quite the same because they do still have pauses in there. So they've got like a 20 millisecond pause that they have in there. We don't have pauses at all. So there are some differences, but yes, they kind of caught up with that in OpenJDK. Similarly, if you look at what we've done with Ready now in terms of the profile, a lot of the ideas that are being included in Project Leiden that's being developed in the OpenJDK and ahead of time things that they're doing there, a lot of those things are basically straight out of what we've done with Ready now. So we are seeing a lot of situations where OpenJDK is looking at what we've done and going, oh, okay, that's actually pretty cool. Let's bring that into OpenJDK. We still have a number of things that we can offer which give us better performance and so on, especially around Falcon. But yes, there have been things that have been adopted into OpenJDK based on what we've done.
Awesome, amazing, really amazing. Are we going to see a very soon like JVM without garbage collection? Do you forecast this?
No, not at all. I mean, technically, you could argue that there is actually a JVM without a garbage collector. It's called the Epsilon collector, which was introduced way back in like JDK, I don't know whether it's like 13, 14, something like that. But it's essentially a no-op garbage collector. The problem with that is, of course, unless you have an application that generates no garbage, you're going to run out of memory pretty quickly. So you hit an out of memory error.
Yes.
So the fact that we can have a garbage collector built into the JVM is very important. It's a fundamental feature of the JVM. So if you don't want to be doing garbage collection, you want to be doing static compilation.
Yes, absolutely. That's why Go is, I think, without garbage
Exactly.
collection.
Yes. Yeah, there are other languages which use a different approach, don't use garbage collection. Yes.
Sorry, last question, if you don't mind.
Sure.
Sorry for taking the time. Is there any correlation between GraalVM and the guys what you're doing, or there's totally different things?
They are quite different because if you look at Graal VM, there's kind of two parts to that. One is the Graal VM itself, which is where it basically runs on top of OpenJDK. So it doesn't really do much that's different to the way that Hotspot works. The big difference there is that they do have a different JIT compiler. So they replace C2 with what they call the Graal JIT compiler. But the thing that people have looked at with Graal, which has been certainly something that has been quite interesting to a lot of people, was the idea of native image. And that's where you do take your Java code and you compile it directly into native instructions. So there is no JVM involved. It still has to have a garbage collector. And they use what's called the substrate VM, which is a sort of a VM functionality that you can compile into a statically compiled application that does some form of garbage collection so that the Java code will work in the same way. So there is that kind of idea. So native image has been very popular with a lot of people, but I don't think it's really delivered on a lot of the promises that people thought it would. It's great for certain types of applications. So if you've got short-lived applications like AWS Lambda, what they call serverless computing, then yes, native image is great because it reduces the footprint, very fast startup, no worries. But if you've got longer running applications, it won't deliver the same level of performance you can get through JIT compilation, and there are other issues around things like reflection and so on.
Yes, I see. I'm sorry, last two questions, if you don't mind.
No, that's fine. I'm enjoying this. It's great.
Thank you so much. So what's your advice for the Java engineers if they want to go deep dive into the JVM and internals and to understand it in a better way?
Yes.
In references, yeah.
So there's quite a lot of materials available. The one thing I would say, if you're interested in finding out more about how the JVM works internally, if you look on YouTube, there are recordings from a conference that Oracle runs each year called the JVM Language Summit. And that's where a lot of the engineers who work on the JVM itself will come and present. And there are people from other companies. So Azul sends people along to talk about what we're doing, and other companies as well. But there's a lot of really good talks by the people who are actually developing the internals of the JVM, and that goes back several years. So there's all sorts of talks on different aspects of the JVM. That's a wonderful source of information to learn about different aspects of the JVM.
Awesome. Is there any a conference dedicated for JVM? Like, does this happen yearly?
Yes, that's the one I say. So if it happens in California, it's the JVM Language Summit, JVM LS. If you look for that, you'll find that it happens once a year. There are a couple of user groups as well that focus more on the JVM rather than the Java side of things, but JVM LS is the big one.
Okay, if someone let's say is new into the JVM part, what would you advise him? Any series of books or any easy book to understand?
Yeah, there's not a lot of books that have been written on this subject. There's one. I'm trying to think who wrote it. Give me a second. I'm just going to disappear for 1 second.
Sure. Sure.
Right. Yeah, this is the book. It's actually quite old because it says Java 2 on it. I don't know.
Yes.
You can see that. But it's by Bill Venners. Yeah, so Java 2 virtual machine. Like I say, it's quite old, but a lot of the ideas haven't changed. So if you want to understand about how garbage collection works or how JIT compilation works, a lot of the basic ideas are in there. It's quite a big book actually, so it's a good solid tome. But yeah, unfortunately, there's not really many books that have been written. But again, if you search on things like the Java virtual machine, just on Google, there's quite a lot of articles that have been written on some of the newer things in terms of JIT compilation and so on.
Nice, awesome, very good. I'm almost done with the questions, but there is one simple request from the community. If we are looking forward in the future to do a simple workshop to check the Java internals and the JVM and this stuff, so we can have some hands-on. Would you support this idea?
Oh yes, absolutely. Yeah.
Thank you so much. Simon. It was really a pleasure meeting you. It was amazing, really session. I wasn't expecting this depth, really.
Good. I'm glad you enjoyed it.
Yeah. So if you have any final words, please, it's yours.
Yeah, I'd just like to say thank you very much for having me on. I was very happy to see that there is a Java user group in Saudi. And so hopefully one day I will be able to come and present in person.
Sure.
So I very much like to visit your country and see what it's like.
Sure, really.
And meet the Java developers there. So hopefully that will happen at some point in not too distant future.
Yes, sure, sure. Thank you so much. Thank you so much, guys, for your joining. And looking forward to seeing you, all of you, once again. Thank you so much, Simon.
Okay, great. Thank you very
Uh,
much. Bye
Have a
bye.
nice evening.
Bye
Bye bye.
bye.